Hello dear students, welcome you all. Students, in today's lecture we are going to discuss the next application of Maxwell relations, right? In this lecture we are going to discuss the effect of pressure on a material. Clear? Uh, for this, we are going to make the use of Maxwell's fourth equation. Right. We know what is the Maxwell fourth equation. It is curly S upon curly P T constant temperature that is equal to negative curly B upon curly T constant pressure. Right. This is Maxwell fourth relation. Right. And this is equation number one. So in case you forget Maxwell relations, then we know the trick P, B, T and S, right? First, second, third and this is a fourth. First, second, third, fourth. First and fourth are negative, right? So it is clear from here that this is negative. So by making the use of this Maxwell fourth equation, we will drive a equation, yeah, a relation we can say, that will tell us the effect of pressure on a material, whether the material expands on heating or it contracts on heating, right? So we proceed further, multiplying this equation on both the side with temperature T. Clear? Then this will become like this. Now I am taking this T inside this bracket. So it will obviously become, if I take this T inside, then it will become here, it will become T curly S. We know uh, from the second law of thermodynamics, T ds is equal to dq, or we can say T curly S is equal to curly Q. So now I am going to replace this equation with curly Q upon curly T at constant temperature, that is equal to minus T curly B upon curly T constant pressure. This is equation number 2. Clear? Now we know very well that the volume coefficient of expansion, if the material expand, clear, then it is volume coefficient of expansion is defined as alpha is equal to 1 upon V curly B upon curly T. Clear? This is from the knowledge of the thermodynamics. Clear? This relation. So here alpha is coefficient of expansion, volume coefficient of expansion. Clear? So obviously curly B upon curly T at P constant pressure will become alpha B. Clear? So now I am going to put this in this equation. So when we will put it here, this will become, your equation will become curly Q upon curly P temperature T, that is equal to minus T alpha B. This is equation number 3. Now this is the desired relation or equation that we were looking for in the beginning. Now we have derived this relation. Now here, now we are going to make the interpretation of equation number 3. Now alpha is what? Volume coefficient of expansion. So if alpha is positive, means the material expands on heating. So in that situation, here the right hand side of equation 3 is negative. So what does it means? Now, if this is to be negative, then what is the requirement? Requirement is if delta P, or we can say curly P, is positive. Clear? Means pressure is applied on the material. Pressure on the material increase. Then delta Q, curly Q, that should be negative. Clear? What does it means? Clear? It means that heat is taken away from the system. Clear? It means it. Clear? When delta Q is negative, it means heat is coming out of the system. Clear? So what does it means? It means when we apply pressure on a material, on a substance that expands on heating, then the uh, on the application of pressure, heat will be generated. Heat will be produced. Clear? When we apply pressure on that material. Clear? But the requirement is what? The requirement is the material expands on heating. Similarly, if we case the reverse, means pressure is negative, then in that situation delta Q will become positive. Clear? So this is the meaning of this equation. Now in case of rubber, okay, in case of rubber, this value of alpha is negative. It means, now what does it mean? This relation number 3 is positive. It means if delta P is positive, then delta Q should always also be positive. Means heat is going to be added in the system. If delta P is positive, then delta Q is also positive. It means cooling will be produced. Then we will apply pressure on the rubber. Clear? So this is the reverse of this material which expands on heating. We know rubber contracts on heating. So the things will get reversed. So this relation equation number 3. The this is the reason why the material expands on heating and contracts on heating, and what happens when we apply pressure on those materials. So all these things are explained on the basis of equation number 3, right? Now we can make even the further interpretation of this equation number 3. This equation number 3 tell us that a material that expands on heating, then in that case, when we will apply pressure, delta P is positive, heating effect will be what is the reason behind it? Now we have to look at the reason. Reason is very clear. The material expands on heating. Suppose this is a small length of that material which expands on heating. So I have added heat delta Q to this system. Then this system is now having its length increased. Earlier it was L, it is now L dash. When the heat is added to this system, this material, its length is increased. It expanded on heating. Now, this system has acquired additional heat energy. Clear? So when I will apply pressure on it, clear? Pressure on it, what will be there? The length of the material, this will get compressed. Clear? It will having now a new length L double dash that is less than L dash. Now in that situation, the extra amount of heat that has been acquired by this material on heating, that will come out of this material. So that's why when we apply pressure on this material, heat is coming out of it. The material getting heated. Clear? And situation will be reversed in those material which contract on heating. For example, as I have taken the case of rubber here. So this is the reason when we have expanded a material, we have done some work, we have applied some energy. But when we are applying pressure on that material, obviously that extra energy, that amount of work is going to be coming out of that material, right? So this is the reason behind it, and this is the full interpretation of this equation number 3. This is very, very important relation. So by making the use of Maxwell's fourth equation, we have derived this equation number 3, and this is the full interpretation of this equation number 3, right? Now I'm coming to the next application of Maxwell's equation, that is adiabatic stretching of a wire. Clear? Adiabatic stretching of a wire. Adiabatic stretching of a wire means we have given a wire, right? And we are stretching it adiabatically suddenly. Clear? So for it, let's consider, we are going to check what will happen when the wire is stretched adiabatically. Clear? So for it, we can take wire here. Right? So this is the wire that is hanged from a fixed rigid support. This is the rigid support. This is the rigid support for hanging this wire. This wire has length L. Clear? And we are applying pressure, or we can say force, on this wire in this direction. So when we apply force, obviously the length of the wire will change. Clear? We are stretching it adiabatically in this direction by applying a force. Then let the length of the wire is changed by amount dl. Clear? Right? When we have applied force here, the amount of work done, that is dw, is equal to minus f dl, force into displacement. Here I have taken this negative sign here because here work is done on the system. Clear? It is not done by the system. Now this wire, right? This is a system. This wire is a system, and work is done on the system. So that's why we have taken this work as negative. Clear? We also know that in the case of a gas, dW is equal to PdB. If it is equation number 1, equation number 2, then we can compare these two equations. So from the comparison of these two, we get P is equal to minus F and V is equal to L. Clear? So this is the difference between these two equations. Now I'm going to make the use of Maxwell's third relation. Clear? Third equation, that is curly T upon curly E S, that is equal to curly B upon curly S P. This is equation number 3, and this is what? This is Maxwell's third relation. Clear? So in this relation, in equation number 3, I'm going to make the substitution these. Clear? And this. Clear? Here in equation number 3. So P will become minus F. So you can see here now curly T upon curly P means F. S, it is minus, that is equal to curly L upon curly S. It was P, so P is equal to F. So here it will become F. Now this is equation number 4. Clear? What I did, I took the Maxwell's third relation, and in that relation I replaced Py minus F and Vy small l. Clear? So now I got this equation. Now I can modify this relation. Curly T upon curly F S is equal to negative curly L upon curly S F. Clear? I took negative toward this side. Even then, I can replace this equation minus curly L upon curly T F into curly T upon curly S F. Clear? There is nothing wrong in it. I simply wrote this side in the expanded form. This we know very well now that curly L upon L divided by curly T, that is equal to eta. Clear? Coefficient of linear expansion of the wire. Of linear expansion of wire. Clear? This is from the knowledge of thermodynamics. Eta, right? So obviously curly L upon curly T will become what? L into eta. So curly L upon curly T, here it was F was also there, so it will become F is equal to L into eta. Clear? Now I am going to put it here. Clear? In this part of this equation. So when you will put it here, you will get curly T upon curly F S is equal to now you have what? You have minus L eta and bracket curly T upon curly S F. Clear? That this is equation number 4. It is equation number 5. Clear? We know very well that curly S upon curly T into T is equal to Cp. This is again from the knowledge of thermodynamics. Cp is specific heat at constant pressure. Clear? So this is T into curly S upon curly T at constant pressure. You can say specific heat at constant pressure is defined as this equation. This is from the knowledge of thermodynamics. So from here I got curly S upon curly T is equal to Cp upon T. Clear? If I invert this equation, then because we require it here, so it we have to invert curly T upon curly S. So obviously curly T upon curly S will become T upon Cp. Clear? Let this is equation number 6. So we are going to put it in equation number 5. Clear? But here it is F and here it is P. But you know, pressure and force are related to each other. Pressure is defined as the force per unit area. So we can put it here and we can write simply, you know, P here. There is nothing wrong in it. So when you put it here, you will get curly T upon curly F S is equal to minus L eta into T upon Cp. Clear? This is now the modified equation number 5 after putting this value here. After putting equation number 6 in equation number 5, then let this is equation number 7. Clear? Now I can write it in the simplest way. dt upon df minus L eta t upon C. Now I write it in the form of full derivative instead of partial derivative. So now this equation 7 becomes this. Clear? Here Cp is what? Specific heat of the material. So it can be written as a small m. If m is the mass of the wire and C small Cp. Now it was capital Cp. Now it is a small Cp. Small Cp is a specific heat per gram of the material. Clear? And this is the total amount of a specific heat. Clear? Capital Cp. So if we multiply this m mass of the wire with specific heat per gram, then it will give the total amount of heat added to the wire or taken from the wire. So right, so this will become now minus L eta T upon m Cp. Clear? Into not into, but this is dt upon df. If I took df toward this side, then it will become dt is equal to minus eta t upon wc into df. Here w is equal to m upon L, mass per unit length of the wire. Length of a wire. Clear? So now this is the required relation that we were looking at. Now we are going to make the interpretation of this relation, this result. I am giving this name equation number 8. So what does it means? As we know, eta is what was eta? Eta was the linear coefficient of linear expansion of the wire. Clear? So now we are going to discuss the different situations, right? So what is the meaning of this equation? It means dt is negative. Clear? For the given positive value of df. Clear? So if pressure on the material is increased, clear, or tension in the material is increased, then dt is negative. Means cooling will be produced in the wire. But the condition is eta should be positive. Because if eta is positive, then this relation is negative. So for many material substances, eta is positive. So when eta is positive, it means dt is negative when df is positive. When the tension, when the pressure in the material increase, it is stressed adiabatically, then cooling will be produced. dt is negative. Cooling will be produced in that material, right? But if we take the case of rubber again, so for rubber, eta is negative. Clear? Eta is negative. Negative means if eta is negative, then this expression becomes positive. Clear? So this expression is positive. What does it means? dt is positive when df is positive. It means if a rubber band of is stressed adiabatically, then what will be the effect on the rubber? It will get heated. Heat will be produced because of this relation, because of this result that tell us that the material that expands on heating will show this type of property, but if the material contract on heating, then it will show this type of property, right? Again, we can make the another explanation of this relation. Why the wire, this was the wire, why this wire is getting cooled if it is stressed adiabatically? Why the cooling is produced in the wire? Now, very simple. The same thing is there when you expand a gas adiabatically. I have taught you in the class also that if you have a gas contained in a container and you expand that gas adiabatically, cooling will be produced in the gas. Why? Because when you expand or in this case, particular case, stretch the wire, then there is no time for the system to get heat from the surrounding. So what will be the then in that case, from where the heat will come? This system will utilize the internal energy of the it's a molecule in this case of gas molecules, and in this case it will utilize its own energy of atoms, molecules of this wire, internal energy, right? So what will be the effect? Ultimately, the temperature of these gas molecules or the temperature of these atoms or molecules will reduce because they didn't got energy from the external sources, from the surrounding, right? So that's why in the same case, cooling and cooling will be produced. You have seen in the case of gases, I have given you many examples. When we expand gases adiabatically, they get cooled. The same thing happened here because they don't get the energy from the surrounding. They are going to utilize their own energy, right? So this is the application of Maxwell's equation for a wire that is stressed adiabatically, right? We take the two cases. In one cases, we take eta as positive, and in other case, we take eta as a negative. So we discussed both the situations, and we arrived at the conclusion that a material that expand on heating, when it is expanded adiabatically, then cooling will be produced. Whether it is the gas contained in a container or whether it is a wire stressed adiabatically, right? So this is all about it. So in this lecture, we have discussed the two applications of Maxwell equations, right? So thank you very much.